So how would you do integrating the 7th power of 2x minus 3?
I would do reverse chain rule because it's not worth doing the binomial expansion.
No, quite. Yes. Right.
So yeah.
So can you go straight for it, or does it help to?
It helps to think a second. I think. Right. So we would get.
So what's differentiating to give us 7th power of that? Like that.
2x squared minus. Oh no, sorry. Out of first. We would get. There. Okay. Something to the power 8.
Yes.
An 8. Yeah. An 8th 2x minus 7 to the power 8. Yeah.
Yeah. Are we done?
No, because it is,
so that's I beg your pardon. That's our dy du.
2x minus 3.
And then the du dx, the derivative of the inner function.
Times 2.
Yeah.
X minus. No, yeah, no, sorry, no, just 2.
Yeah. In which case?
You get a quarter. No, sorry, but no, we don't. 2. Oh, so we need to divide by 16.
That's right. Up here, at least, we do.
Yes.
That's what you meant. Yeah, quite. And then you can check straight away by differentiating. Say to yourself, if I was differentiating that, I would say 8/16 is a half of that blob to the power of 7, and then I would multiply by 2, so everything's correct. Add C.
Yeah.
Okay.
Yeah. And that's it for that. It's just.
Yeah. Okay. Next one is.
Next one is. I haven't seen. Yeah. X root. In this case, we would have to. That would be a chain rule again.
So
with the inner function being 4x minus 1 and the outer function being the square root.
Okay. Power of a half.
Yep. So you would have come from something to the power 3 over 2.
Yeah.
And then you would have that divided by divided by 3. No, sorry, times by 3. Oh no, sorry. Is it times by a half, or am I?
Well, it depends what else is going on. Just on account of, with respect to the inner function, anything to the power of a half integrates to, with respect to that thing, it integrates to how many of that thing to the power of 3 halves?
Mm-hmm.
How many? What coefficient do we want here?
We want
so far.
Oh no, sorry. So it would be something that times by
I mean, if that was just x,
something that times
if
by
you were integrating x to the power of a half, what would you get?
x to the power of half, you'd get x to the 3 over 2, and then you would get that divided by, no, sorry, times by 3 over 2.
Okay, let's test that by differentiating. So pretend you're differentiating that. What would you do?
You would you would
Yep.
oh no, so you'd add the power, so you take away the power and then multiply by 3 over 2. So you would get yeah, so you'd get x to the half, and then that would go to, oh no, it wouldn't, it would be 9 over 4.
Yeah, you would multiply those first and then reduce the power by 1, wouldn't you? So yeah, you'd have 9 over 4, so that didn't quite work. Let's try again, integrating x to the power of a half. What would differentiate to give you x to the power of a half?
Well, it will be x 3 over 2. Like
that has to be the power, doesn't it?
Yeah. And then whatever times is by 3 over 2 to make 1.
Exactly. Yes, that's the way to think of it. Yeah.
Yeah. The thing is, I can't think of. I was struggling to think of exactly what that would be.
Well, I mean, it's the right question to ask. What can you multiply by 3 halves?
Oh, 2/3.
2/3, exactly. That is the way to think of it, though.
Yeah, no, that's fine. I was just wasn't thinking the right way about the fraction, but yeah.
Okay, so over here, we might put a 2/3 there, even if we think it'll do for now anyway, you know.
Yeah.
And then we'll test by differentiating this and seeing what happens.
Would we not? No, because we've forgotten the x on the outside. Actually, no, because we obviously in the original you've got x root 4x minus 1. X would have come from it.
So what will we get if we differentiate with this? Differentiate that.
We will get half. No, sorry, we'll get 4x minus 1 to the half.
Yeah. That would be the dy du.
Times 4.
And then times by 4, which is the du dx, yeah? The derivative of the inner function.
Yeah.
In which case?
In which case, we would change the 2/3 to 8/3, whatever that is.
Okay, let's test that.
Right.
Pretend we're differentiating 8/3 of that stuff to the power of 3 halves. Go ahead. What would you have?
You'd have that stuff to the. Oh no! Sorry, no, you wouldn't have that. Oh, actually, no. Wait, would you? 1 second.
I mean, let's pretend we're differentiating 8/3 x to the power of 3 halves. What would we get?
It would get x to the power half.
Yeah. How many?
And we would get that. 24 sixths, so 3. No, sorry, 24, so 4.
4. So we would have a 4 here. And then we'd need to multiply by 4, which is the derivative of the inner function.
Oh wait,
So we're ending up with 16 times the square root.
no. So we don't want to do that.
No, let's go back a bit. But this is quite normal to have to backtrack. And it's good to be testing this way, to be going backwards and forwards. You do want to look backwards and check by differentiating all the time.
Yeah. So okay. Yeah. Right. So you've got that times 4, and that's what that goes to. What are we even trying to get to? Oh no, sorry, we'd have to divide by 4. So we would
That's right. So look at this 4 here and think, I want to cancel that, don't I?
yeah, so we'd get a 6th.
Yes, that's right. We would indeed. Have a 6th up there. So how's it working now?
Well, we are missing we're missing dx.
Yeah.
Which
So
we just put on the front as x as half x squared.
So put it here, you mean? Oh, I see what you mean. So let's multiply this by half x squared.
Yeah.
Half x squared times all of that.
Yeah.
Because then this would differentiate to x rather nicely.
Yeah.
Okay, but can you see why that doesn't work?
Oh no, because it ends up in the. What does it? Do you have to put brackets around the other stuff?
Well, you would have, yeah, we would need. I'm not sure we would actually need brackets, but I mean, we've already got brackets there for sure.
Yeah.
But the x squared is going to cause problems because if you're differentiating x squared times any other function of x like that, and then we've got, well, what have we got? A 6. So in total, we've got a 12th. The 12th is fine. But the x squared is going to cause problems, isn't it? If we imagine we're differentiating that, because we've got to apply the product rule, haven't we?
Yeah.
You don't have to apply the product rule if it's a product of a function and a constant.
Oh, well, it's the product of 2 functions.
Yeah, it's a proper product. It needs the product rule. So it would differentiate to something very different to that.
Right. The product rule is. Oh yeah, you different. Okay. Yep. So it would be half x squared times root 4x minus 1, and then that. Can you see what I'm trying to say?
No, are you at this level or the top level?
No, the bottom level.
Right.
Because
okay,
seeming as it's a product rule,
yes.
Yeah, you would.
Well, if you're starting to treat it as a product rule problem, then great, yes. So in other words, we're going back to that stage where you said.
Oh wait, we made it so. Yeah, no, we could have made that so much easier. Anyway.
So let's treat it as a product rule from the word go. Yes.
Yeah. Okay. So one of them would be x, and then what was the Okay, so in the top row.
Yeah. Already.
One of them would be half x squared,
Yeah.
because that obviously differentiates to x.
So you're going to integrate x, fine. Okay.
Then root 4x minus 1 was a chain rule. So it would be to the half and then times by 4.
Sorry, you've lost me now. So you're putting a x in there and the square root in here, yeah?
Yes.
Then you've integrated that one. It's a product rule, so...
Okay, and then then you'd get half x squared times the whatever that went. What's that again? It was 2 on
Yes,
the...
I'm sorry, I've rubbed out the whole of that previous attempt now, perhaps. But don't forget, what we've lost all evidence of was a valiant attempt to integrate that. Now notice I've left that the same up here. I've written it differently as power of a half. But we've left that alone now. Now we're differentiating that rather than integrating, which is what we did last time to that expression.
Oh, right, yeah, okay. So we would... we're differentiating, so we would get minus a half.
The power would be minus a half, yes.
Powers would be minus a half, so you would get 4x minus 1 to the minus a half. Yeah. And then you'd have to times minus a half by a half, so you'd get minus a quarter.
No, you've lost me.
Have I?
So yes, we're differentiating 4x minus 1 to the all to the power of.
Oh no, sorry, we're differentiating, aren't we? So we don't need to. So it'd be a half times a half, so a quarter. Well, actually, no. Sorry, we'd get 4.
We would have to multiply the bottom by 4. That's right.
Yeah, okay.
So it would simplify to 2 over the square root, basically.
2 over the square root,
yeah. Yeah.
And then
so we've got 2 over the square root. Yes, sorry. Now would come the adjustment. It's integration by parts, isn't it? And now we would be saying, okay, let's subtract whatever it is this unintended consequence was. Okay, because we want the whole thing to be still equal to x times the square root.
Yeah.
So this has come along uninvited, kind of, and now we need to subtract it. So what are we subtracting? Gosh. Well, actually, both of these halves cancel all of the 4, so that's good news.
What do we
so all of the constants disappear. They cancel.
Have I done integration by parts? I may not have, because that may be...
Oh, really?
I get a feeling...
Oh, yeah, sorry. Maybe we haven't done this. Oh, wow! Have we not done work backwards through the product rule before? Yeah, pardon me for forgetting.
Not with the product rule. I mean, I thought it would be similar to...
No, all we've done so far is the chain rule, probably, if I go and look now.
No, we've only done the chain rule in my memory, so even if we have done the product rule, it hasn't stuck.
We probably haven't. Oh, right. Okay. But you know what I mean by that shape for the product rule, you know, differentiating one, leaving the other alone?
Yes. The product
rule
itself.
Well, that's what integration by parts is. So, you know, it's not that bad. In a way, it's easier than working backwards through the chain rule, in a way, because you can follow the process of trial and improvement graphically.
Yeah.
All right, so let's get our bearings. We were trying to integrate this, weren't we?
Yes.
So we put that in here and we said, well, maybe we've got a product rule situation. So you filled this in, well done. But now we have to fill these in as well. So what we found the integral of is not quite what we started with.
No.
What we found the integral of is all of this, and the integral is this.
Yeah.
So how can we turn our starting stuff back into what we had if we've added all this stuff?
Take that stuff away.
Take that stuff away, and then the bottom row will return to being what we were trying to integrate. Now, these constants are all cancelling, so that's quite nice.
Yeah.
Right. So if only we could find the integral of what's left here, which is that, isn't it?
Yes.
So now that this bottom row is once again exactly what we were trying to integrate, because we've added stuff, but then we've taken stuff away. If we can get a top row which differentiates to give the whole of the bottom row, then we'll be laughing. So if we can only find the integral of this and put it here.
Oh, okay. No, that makes sense. Yeah, right. So the integral of that, what would differentiate to make that? Well, it would have to be something to the power half because it goes to minus. No, it wouldn't.
Yeah.
It would, yeah.
Okay, so you can start experimenting with stuff like 4x minus 1 to the power of a half, and then see how that differentiates. Does it give us anything like this? But we can see what it gives us. It gives us something very like that. But the x squared didn't come from there. The x squared was coming along anyway. So it doesn't look as though we are going to be able to differentiate that to give us that. So actually the integral of that is beginning to look quite hard.
Yeah.
Now this is a very typical situation in integration by parts. I don't want to put you off, but it does often happen with integration by parts that you get about this far and think, could I have gone about this slightly differently at some, I mean, did I have when I had a straight choice, let's go back there. When we were here, or even before that, because you went straight away to integrating x here, didn't you? But if we look at this situation, we could do it slightly differently. Because we ended up in a spot where, well, we had a harder integration problem really than we had here. I mean, x times that stuff is hard enough. But over here, we were trying to deal with x squared times that stuff, which looked even more daunting.
Yeah.
So maybe when we're looking at this product rule, we could approach it. How do you think? How could we fill out the rest of the product rule a bit differently? So you made a choice, didn't you? Really, you might not have been aware of it, but you definitely made a choice when you said, okay, well, I know the integral of x is half x squared.
Oh, right.
So the other option was what? You see, remember with a product rule, it's always the top is differentiating by doing one at a time, leaving the other one alone. But it doesn't matter which way round you do it.
Oh,
there's the choice always with the product rule. On the way down, it doesn't matter at all, does it? Because you just add, it doesn't matter which way you present it. Whether you present the first one left alone and the second one differentiated, followed by the first one differentiated and the second one left alone. Or the first one differentiated and the second one left alone, and then the other way round. Are you clear what I mean by the product rule, by the way? Oh, have I lost you, by the way? Oh, I think we've lost the signal, haven't we? I think. In which case, I'll just hope that you can hear me again in a minute.
Yeah, we were doing the...
Right, now I don't know, it took me a while to realise you weren't there, so I began to ask whether you are quite familiar with what I mean by the product rule and representing it like that. Does that say the product rule to you?
No.
Okay, so if one of them is called u and the other one is called v, we say the derivative of uv is u dash v plus u v dash.
Oh, is it? You mean as in? Oh no, sorry. Yes, it does. Sorry, it does. It does. No, that does work. Yeah.
Okay. Now, what we're doing in integration by parts is just working backwards through that rule, just like we can work backwards through the chain rule.
Mm-hmm.
But we have to be a bit more systematic than with the chain rule, where we can do a lot of it mentally, or what they call by inspection.
Yeah.
So we don't often work backwards through the product rule just by inspection. We never do. We never do. We always want to, I mean, there's a formula which we'll discuss, but this is what it represents. So the point is, you've always got a choice with the product rule as to whether you are differentiating this one and leaving that one alone, and likewise there, or whether you are choosing the other way round, differentiating this one and leaving that one alone, and then the other way round there.
Mm-hmm.
Do you see what I mean?
Yes.
Okay,
Yeah.
so with the product rule, is it that way?
No, sorry, actually, sorry. Are you?
Yeah.
No, sorry, because the on my screen for some reason I can see the textbook, but like over the
What?
which I don't get
That's
at all.
mysterious.
I can see the textbook questions.
Oh my lord, that shouldn't be happening. Oh, I see, I've lost the sharing of the screen, perhaps. No, if you're seeing...
Maybe you should restart the sharing of the screen and see what difference that makes, because I'm seeing the textbook page, and the only reason I responded when
that
you said
screen wasn't even up. Yeah, sorry.
No, when you said the product rule is because the mouse coincidentally ended up near the cos x plus
Oh
sin
my
x.
god.
So,
right. Yeah, I've never known that happen before. Can you see it now? You see the
yes,
work now?
I can see it. Yeah. Okay.
All right. What I'm trying to say was, if that's the product rule, and which you recognise as the product rule, yeah, with the u and the v. Oh, did you not? When I said u and v before, did you not?
I recognised it just from you saying u and v.
But I thought we were looking at this. You see, uv there differentiates to u dash v there plus uv dash there.
Yeah.
But I could have put it the other way round. I could have said uv differentiates to uv dash
and
u dash v.
U dash v, yeah.
So that's always a choice with the, and there's no way of getting around that with integration by parts. You've got to, there's always a system which is, you know,
Uh-huh.
which I don't. Most people rise above it one way or another. You know, it's not too notorious. I'm just saying it's got to be dealt with. So anyway, that choice there before, I think you just assumed, oh well, I've got to integrate x to get x, half x squared, but as though it was that way. But it might be the other way around. It might be that we are integrating the other part of it
Yeah.
and leaving the x alone.
Yeah.
Do you see what I mean?
Yes.
And we're
yes.
going to differentiate x.
Oh, yes. No, okay, that's... wait, and then we're going to differentiate x, and once it's differentiated, what do we have to subtract?
Something simpler, because x differentiated is what?
X differentiated is x squared. No, sorry, no. It's 1 over x.
Is it?
Oh, no, sorry, am I being...
Derivative of x with respect to x?
1. It's 1.
It's just 1, you see. So this unwanted consequence here that we're going to have to subtract is going to be a lot simpler this way round.
Okay, right, yeah.
As long as we can
differentiate,
integrate
not
this one here and put it there. And of course we can, because that was our first try, wasn't it? To look at this as integrating precisely that.
Yeah.
And we got some way with that, didn't we?
Yeah, we did. We were almost there, and then we realised that there was the x there.
Yes, and I shouldn't have destroyed the evidence. Can you remember what the integral of this turned out to be?
No, it was. So
it was going to be. Yeah, sorry.
It was 2 times. Actually, no, was it 2?
So we've got blob to the power of a half. Anything to the power of a half integrates to
3 over 2. Blob to the power of 3 over 2.
Yes.
And then.
So what would the coefficient in general be if the new power is 3 over 2?
The coefficient would be. It would have to be 2 over 3. Yeah, it was.
Yeah.
Oh yeah, so we got. Yeah.
But then when we considered differentiating that perfectly respectable first guess,
yeah,
we found we got not quite this. If we differentiate from here down to here,
we got that times 4.
Times 4. So the appropriate adjustment up here was which?
To make 2/3 to a 1/6.
Exactly. Well done.
Yeah. And then.
Now let's test that by differentiating. What's 3/2 of a 1/6?
3/2 of a 1/6.
God, that's not easy, is it?
2. No, not 3/12. So a quarter.
Yes. So a quarter. So we're going to have a quarter blob to the power of a half, because half is 1 less than 3/2. So we've got a quarter of all that, but then of course.
Then of course we don't have what we originally had.
But we would, because on the way down, you see, from here to here, we need to multiply this by
4.
The derivative of the inner function, which is going to cancel the quarter.
So yeah, okay, that's fine.
So you see how looking up and down all the time and continually adjusting, you end up with something which is perfectly good. We've got exactly the integral of that up here.
Yeah.
And we've tested by differentiating. And we get exactly that on the way down.
Yeah. Yeah. Okay, and then the...
So in here, we write what?
A 1/6, 4x minus 1.
Yeah.
To the power of 3 over 2.
Yeah.
And then what we need to subtract is it that?
Just that, isn't it? Times 1. So it's got to be exactly a 1/6 of 4x minus 1 all to the power of 3/2.
Hmm.
And that is not really any harder than this one.
No, it's not.
It's similar in
That was,
nature. We can tackle it in exactly the same way by saying, okay, anything to the power of 3/2 is going to end up here being the same inner function to what power?
sorry that I didn't quite. I didn't hear that end bit because the connection did something weird. But what did
By
you
the way,
say?
do you ever want me to send you the picture of this?
No, because it's all right because generally it means that no, I'm okay because I write a lot of it down anyway.
Well, I know.
But
Good. I mean, that, and I don't want to discourage that, but on the other hand, um, if you want me to send you the picture and it means that you can, I don't want to say write less as though I want you to be writing less, but anyway, it's an option anytime if you
yeah,
want me to send you these pictures. Right.
mhm.
So what are we going to have up here?
Is that power wise or is it?
Well, it's up to you however you want to look at it. But yes, when you're going from bottom to top, when you're integrating, you do generally decide the power first, don't you?
Yeah, so I would say that would go to 5/2, and
Yeah.
then 5/2 to make it 6 times 5, 30/15 on the front, or am I
Sorry.
jumping ahead? I'm trying to think of what would go on.
Yeah, that's fine. You might be doing the arithmetic. I would tend to, immediately I've thought of the power, I'd think, okay, coefficient of 2/5 and subject it to what adjustments on account of, oh, a 6th. I want 2/5 of a 6th. Oh, yes, you said a 15th, didn't you?
Yeah.
Okay, good. And then what other adjustment do we need?
We need to multiply. What other adjustment do we need? Oh, no,
So let's put that in. Let's test. Let's test a 15th of all that stuff.
Yeah. Uh-huh.
What's
Yeah,
5/2 of a 15th?
5, 1, 6.
1/6. That's what we want. And then we reduce the power by 1. So it's all working well.
Yeah, but we have to times by the inner.
In a what?
The derivative of it.
Yes.
Or no,
Yes.
yeah.
Yes. Sometimes you end up saying inner derivative, which is a bit vague, but it's fine. Meaning the derivative of the inner function. Yes. Being again what?
Being 4.
4. So
a 15th
so,
times 4.
so you want to have 4/15 up here?
Yeah.
Let's test that. Okay. 5/2 times 4/15 would be
20, 30, 2/3.
right. So you'd have 2/3 there, and then
Yeah,
after multiplying by what?
4.
So you'd have 8/3 in the end, wouldn't you?
Would you?
Well, if you had 2/3 here, because you said quite rightly, I think 5/2 of 4/15
Oh,
was
no, sorry.
20/30, which is 2/3.
No, wait a second. We wouldn't be timesing by 4. We would be dividing by 4.
That's right. You see, at the stage where you considered this 4 here, because you have 4 here, that means you want a quarter here really, or wherever you're putting a quarter, and therefore yes, you wanted a 4 on the bottom up there, not the top.
Mm-hmm. Yeah.
Okay. So,
Is that it? Does that?
so is what it?
Yes. No, sorry. Wait. The top row. So
Yeah.
the would you'd have to divide by 4 the whole thing.
So, yeah.
15 times 4, which is 60. Well, a 60th.
Right. Okay, let's test that. What's 5 halves times 1 over 60?
5 over 120. So it'll be 1/24.
Yes. So this would be a 24th blob to the power of 3 halves.
Yeah.
Is that okay?
I'm not sure if it's okay.
It is, because don't forget, we would be soon multiplying by
4.
and a 24th times 4 is
24th of times 4 is. What do you mean a 24? Oh wait, no, 4 24ths. 6, 1 6. No. Yeah.
yes, it is.
Oh, it's 1/6. Yeah, no, okay, that's fine.
So everything's peachy again.
Yeah, okay. And wait, the 1/60th 4x minus 1 5/2 that we've just thing, is that subtracted from the rest?
Exactly. Well done. Yes, that's right. So you're seeing the big picture here, which is that, you know, what we're trying to integrate is the whole of the bottom row, because so much of it cancels. And as long as, yes, although we have the product rule and the chain rule, because not everything differentiates, you know, in the simplest way possible. We can't say the derivative of a product is the product of 2 derivatives. It's more complicated than that, as we're seeing. Nonetheless, the derivative of one thing minus another is always just one derivative minus the other derivative.
Yeah, okay.
That's what's called linearity, incidentally.
Okay. Yeah, no, that makes sense. I think the main problem I had with that is that I hadn't done integration by parts before. So when you said, "Oh, you have a choice as to which one to do," I was like,
"No,
"No,
quite."
you don't."
And actually, I thought we had done this before, because I've done it so much recently, and I apologise. Yeah, that must have been deeply mysterious. Yeah. So yes, up here we now have a sequence of expressions. That stuff there, which is going to differentiate to all of that, but then minus that stuff there, whose derivative is going to cancel some of that. So that it all checks out. Plus C, and we're done.
Okay. Well, yeah. Okay. So that's the final answer, isn't it?
Yep.
All right.
I mean, we can prove it straight away by differentiating it, you know, the whole thing. And if we were differentiating that, well, it would seem to split naturally into that part. We'll differentiate that, and we'll have to apply the product rule. We'll get all that.
Yeah.
And then we'll differentiate that as we've been doing, just in order to be sure of the integration.
Yeah, I mean, we'd eventually get there.
Yeah. Okay. Now, where was I here? All right. Next one. Sine squared x cos x.
Actually, wait a second.
Sure.
Wait a second. There was something that I was going to ask.
Oh yeah, do by all means.
No, I'm trying to think of what I was going to mention because it came up before. Let me just have a look quickly at what I was doing because it was. Oh right, no, sorry. So okay, in the textbook there is on page 300,
Reverse chain rule, yeah,
yeah,
good.
300, there was something on there.
Uh-huh, yeah.
I'm trying to find exactly what it was. Because, I mean, all of those work with the sorry, all of the ones on this page work with the way that we were doing the reverse,
Yeah.
chain the other way around, which is basically finding what would differentiate to.
Yeah, exactly. By all means, find one that didn't seem to work. Yes.
No, it was just you see in the bottom left there the reverse chain rule thing.
Yeah.
What does that mean compared to what we were doing?
It's just a particular example of what we were doing, where and did we do examples like that? Let me try and find one. What were our examples? Here was a nice example. Here's another kind of nice example. Here's another nice example. Did any of them turn out to be? Here's closely related, which is E. And that was cos. But it looks like we didn't do any that were like this, where we were integrating a fraction, and we had, in integrating, we ended up going up to a natural log. That's what's going up on there. And because they're turning that particular case into a formula, that's giving you pause. You see what I'm pointing at here?
Yes, the log x and then 1 over x. Sorry, yeah.
So yeah, if you're integrating any 1 over any interfunction, if the outer function is 1 over basically, then you're going to go up here to log of the inner function.
Yeah.
And then of course on the way down, you will be multiplying by the derivative of the inner function.
Oh, right. Yes.
Which is f dashed. Which is why they're showing you this formula, f dashed of x over f of x, which is precisely that.
Sorry, yeah, that makes. Well, what was the? Did it say k on it as well, or did I just misread?
Well, no, that's saying, but we've found that all along, haven't we? Wherever you're multiplying by a constant, you just take the constant up there.
Yes. Okay.
So as long as it's only a constant, it doesn't require a product rule or anything.
Oh, it's okay. Yeah, that's fine.
All the k is for there, I think.
Yeah, so if it's a constant multiplied by log of anything, then yes, okay.
Sorry, say again.
If it's a constant, yeah, no, I was just.
Well, if it's a constant times, yeah, the constant. The
yeah, no, I was just running it through my head. Yeah, it was
actually
just,
the case of constant is probably what confused you there. They're in the habit of doing that. In the formula booklet, you'll find most of the useful standard integrals and derivatives have got k's all over them, which can be dead confusing.
But
until
I'm
you realise
that I don't need to use the reverse chain rule as long as I.
Oh, what?
I'm assuming sorry, because I'm assuming I won't need to use that sort of.
Well, that particular formula, f dash.
As long as I just do it.
No, I mean, the trouble with that formula is it looks like something new and different. It's just another example of the chain rule.
Yeah.
For this particular case, where you're going up to a log.
Okay, that's yeah. That was it essentially. I think that was the problem in its.
Fine.
in its basis. I think. Okay.
So
What was it
integral of
sine squared?
sine squared cos x.
Okay, so that's a product rule, is it not?
It might be. It's a product. So the question is, shall we pass it as a product for the
Or shall
product
we-
rule,
Yeah.
or shall we pass it as a composite multiplied by an inner derivative, potentially?
How would? Oh,
In other
because it
words,
would be
yeah,
what as in sine squared and then x cos x as the inner. Is that what you're trying to?
no.
Oh
That
no, wait,
we
sorry,
can't pass it like that
that's
without
not
brackets there.
allowed. That's not allowed. Yeah.
Yeah.
Yeah. Okay.
So all I'm saying is, what we've got is sine x cos x, really. So we could look at it like that, or we could look at it like that, or we could look at it like,
All three.
presumably that, or I don't know.
Yeah.
But
Anyway.
also, in a way, we could also look at it like this. Can you see that?
Yes. Yeah. No, because it's yeah. No. But yeah. Yeah.
So
Actually, that's probably the best. I think that makes sense to do it that way. No.
it does, yeah,
Because then you would get.
absolutely.
Yeah. Okay. So if we differentiate, if we're integrating sine squared
Yeah,
x, you would get
with respect to sine x, yes.
a half sine x squared times a half sine x squared times
I mean sine x all squared.
yes.
Where are you putting the half? Up here or down here?
Up there. Up there.
And your power is?
3. Oh, sorry. No. Wait, no. Seeing as it's that, it would be a third. Would not
Yeah,
half.
that's right. So fine.
And then the differential of the inner function is minus cos x.
Or is it?
What am I lying? Sine x differentiates to. It's just cos x, is it? Yeah, it's just cos x. That yeah. No, yeah, that's that. Yeah, okay. And then cos x. So what we need to do. And does that work?
Well, let's test by differentiating. If you had a third sine cubed x.
Yeah, well, you would get sine x squared like that. And then you would, I'm pretty sure you would get cos x because.
That's right. This part of it is dy du in that.
Yeah. And that's
formula,
du dx.
And that's du dx.
Yep. Okay, and now we're missing the cos x from the previous bit, but cos x differentiates to.
Are we missing a cos x?
No, from the original integration.
Are we? The original thing we were integrating was sine squared x cos x, wasn't it?
Mm-hmm.
I don't see what's missing.
Wouldn't it be cos x? No, because haven't we just integrated sine squared x and nothing else? Or am I?
Well, no. We knew that there was more to it. We knew that when we tested the integral by differentiating, there would be more to it. And we were vaguely aware that it might take care of this cos.
Oh no, so no, okay, that's fine. Yeah, no, sorry. I just what I did in my head is, yeah, that's fine. It's because it was our first guess. I almost expected it to be wrong, but it's not really.
Exactly. Yeah.
Okay, that's
Just,
fine then.
sometimes that's all there is to it, you know.
Yeah, that's my mistake. I just didn't notice that. But yeah, okay.
So that's the integral of that one.
That's integral
Well,
of
that was
one.
really quick, wasn't it? That was too easy. Let's try one more. X log x.
Yeah.
Oh, that's fun. X log x is lovely because it's a nice example of something. So we've got x log x. Now log x. Where's log x along here?
Log x. Well, it's
nowhere, is it? We've got a log x up here, but there's nothing in this table telling us how to integrate log x.
That's a good point. I have not.
So how are we going to integrate x times log x? Well, what are the options? What do you suspect?
Product rule?
Yes. And as a product, it's got to be x in one of the parts and log x in the other part. And when I say part, I've never gone to Wikipedia to look up in all my life to check that parts actually refers to parts of a product in integration by parts. I've always assumed it's too obvious, it must be true. So how should we fill in the rest of the product rule?
Well, if we want to, we don't know how to integrate log x, so we
couldn't even if we wanted to.
Yeah.
So we must have to integrate the x.
Yeah. So we would get half x squared.
Good.
And then times log x.
And then?
Log x goes to 1 over x.
Good.
And that's obviously just half x squared.
Right.
And then we would be subtracting.
Good.
Whatever.
Yeah.
That is.
And what is it?
It is x squared over 2x.
Which simplifies to?
X squared over 2x. X over 2.
Yeah, perfect. Which is easy.
Yeah, okay, yeah.
So?
Yeah, so that's basically, it's like when earlier we did the same thing about choosing which one to integrate, but it's in this time it is quite literally. Is it impossible to?
Well, that's right. We're saved having a choice. We might get deep. You know, it's common for this to cause a lot of confusion because unless you realise it is by parts. Oh no, sorry, I'm thinking of something else as being potentially more confusing. So yes, as you say, it's. There's no difficult choice. If it's going to work by parts, it's going to have to work by integrating the x.
Yeah. So.
And so, what happens?
Minus a half x, which comes from. It was something. It'll be x squared up there.
Yeah, it'll be, the power will be 2. That's right.
X
and the coefficient will be
1.
Okay, let's check that. The derivative of x squared is
half x. The derivative of x squared.
No, I don't think the derivative of x squared is half x. No,
it's 2x.
It's 2x, isn't it?
Oh no, it's the same thing as earlier, where you need to divide by.
Yeah. Yeah.
Yeah, so divide by 2 or times by a half. No.
Yeah.
Yeah.
My preference is always at that stage where you're trying to figure out this coefficient, immediately take the reciprocal of the new power
Mhm.
and multiply whatever you had down here by that reciprocal,
Oh, right. So yeah, half x. Yeah.
giving.
Would it be minus? Oh no, sorry, it wouldn't. It wouldn't be minus half. So you'd get a quarter.
Yeah. Which we can test straight away.
Yeah, no, yeah.
2 times a quarter is a half. Reduce the
Half.
power by 1. Of course it works. Yeah.
Yep. Okay. And then
So the integral of x log x is just all of that plus c,
plus c. Yeah. Okay.
which is a nice example of integration by parts where you can see the whole.
Yep.
And incidentally, one to leave with you if you appreciate being left with a puzzle. I'm not sure. What about this one? After all, when we've just agreed that we've got no way of doing it at all. But if I tell you it's by parts.
If you tell me it's by parts, then log x times 1.
Exactly. Yes, which is fun to do. You say, okay.
Oh right, yeah. Yeah, that's yeah, and then you would.
Yeah, you can see what's going to happen up here. One would integrate to.
One would integrate to 1x, x.
X, and then you'd have x log x, and down here you'd have x times
X times log. No, x times 1 over x.
1 over x.
You'd have x over x, which is 1.
So we've just got to integrate 1.
And that goes to x.
X.
Minus
Yeah.
x.
So the integral of log x is all of that.
Why don't they give you that in the? Because that's not impossible to find at all.
Well, they probably do. Yes. I mean, I'm probably spoiling the fun of the next one coming along. You know. I mean, I was going to leave it, but actually, you've done it. So fine.
Yeah. Anyway.
So that would be like that, wouldn't it? Oh God, I can't draw today. All right, and that's basically integration by parts, although I haven't told you the formula, but I won't apologise for that. But I will do the formula.
There's no real reason to learn the formula because it's
good.
Just,
that's
the rule. It's
exactly.
like
you want to understand it. Yeah.
It's not when I did it's not like when I do the chain rule. I type out du dx times dy d. I don't. I wouldn't bother with the.
Yeah. It's hard to know. There's such a variety of different kinds of examples where you could make a different case for this method versus that method. So just be prepared to use whatever works for you from what's available. Yeah, right. Okay.